All right, so today we start organic chemistry. Which is what we're going to be doing for the rest of the semester. Talking about these different kinds of molecules and their kind of unique chemistry, as well as in lab today. So because we switched the lab order, we're kind of getting into organic chemistry now. We should finish that chapter 11 by before the exam. So chapter 11 will definitely be on the exam. It will be a little rushed. So we may go a little long on next Tuesday, because we won't have lab, but we do want to make sure we get through all of chapter 11 before the exam the next week, so you can have the holiday weekend to work on it, on homework for that, and be ready for that. But we're going to talk about that now, and then there's a little bit of chapter 12 at the end also. So what is organic chemistry? Anybody know? Have you taken this before? How is it different? Why does it have this separate category? Have you heard of that? Have you heard of organic chemistry? Heard that phrase? You know what that refers to? What does it mean that something is organic? Alive? Sort of. But you're on the right track. It has to do with life, with organisms. This distinction comes from way back. Scientists used to think that there was organic chemistry, the chemistry of living things, and inorganic chemistry, the chemistry of rocks and minerals and things like that, and that those two had nothing in common. That if a molecule was made, or if chemistry was made in something that was living, a person or a plant or whatever, you could never make that from non-living things, and vice versa. You could never make minerals from living things. We know that's all wrong now. Atoms are atoms. It doesn't matter if they're in a living thing or a non-living thing. The chemistry is all the same. But we keep this category of organic chemistry, and we talk about it as being focused on, we'll say that it's from life, but what we really mean is that we're going to focus on molecules made of carbon, hydrogen, oxygen, and nitrogen primarily. And the big one is carbon. Organic molecules tend to have mostly carbon in them, and then this other stuff also. And then there's other things that we will see. So it's not just those things. There's a bunch of other things in there. But primarily the molecules we'll be working with for the rest of the semester will be made from carbon and hydrogen with some oxygen and nitrogen and some other stuff. So that's what we're going to call our organic chemistry. Now to think about what that means and what that might look like, we want to look at carbon and kind of remind ourselves about how carbon bonds. Does anybody remember from a couple chapters ago, how many bonds does carbon usually make based on its valence electrons? 4, right. It's got 4 valence electrons, which means it needs to make 4 bonds to have a full octet. So we drew a carbon atom, a Lewis dot structure. We could draw its 4 electrons like that, or its 4 valence electrons. And this tells us that there are these kind of spaces where it can also want to have an electron. And that's why it bonds. So it bonds with 4 things, or 4 times. It shares 4 more electrons with other atoms to get its full octet. For instance, with hydrogen, if we had 4 hydrogen atoms, now this isn't really a chemical reaction, because you can't just have free carbon atoms and free hydrogen atoms, but it's more like just a way to think about it. Hydrogen has 1 valence electron and then 1 space, because it wants to have 2 to have a full shell. So these things are going to come together and make this kind of a Lewis structure. I know we've done this before, but good to remind ourselves that that's what that structure might look like if those things come together. And then we might also draw that with lines. We know that a line indicates 2 shared electrons. That is the simplest organic molecule. This is known as methane. 1 carbon, 4 hydrogens, CH4. Now, the way we've drawn that, kind of as we've drawn a lot of our structures so far, it looks like those bond angles should be about 90 degrees. You see that? That like the relationship of one hydrogen to the other looks like 90 degrees. Well, it's actually not. It looks like it the way we've drawn it, but we've missed something about this structure, that this is not a 2-dimensional structure that's flat on a piece of paper. It's a 3-dimensional structure in space. So I'm going to show you using this modeling program. We're going to draw a methane molecule. Let me find my thing here. Here we go. Here. So there's our methane molecule. And you can see pretty clearly this is actually the structure of methane, and you can see that that is definitely not flat. Right? Those angles are not 90 degrees. They're definitely bigger than 90 degrees. And so take a look at this structure, because this is the actual structure of methane. Kind of let it zoom around a little bit. You can see the carbon atom in the middle, and then the 4 hydrogen atoms are on the outside. And try to think about the way in which they are distributed. One thing you'll notice is that this is a very symmetric molecule. All those hydrogen atoms are equivalent. We're making it kind of rotate around that top one, but there isn't really one on the top. We could just as easily put that one on the top, and it would still look the same. So every position is equivalent here. This is a totally symmetric structure. And the name of this structure is, it's a tetrahedral structure. It's a tetrahedron. So I'm going to copy this over. Stop spinning a second, so we can take a look at it in our notes and draw some stuff. Uh-oh. Trying to get it in a particular position here. All right, that's good enough. So I'll cut this out a little bit and put it over here. It doesn't need to be quite that big. Okay. So there's our tetrahedral structure. That's what it actually looks like. So not flat, but rather tetrahedral. And that structure comes from a tetrahedron, which is a shape, in a geometric shape. If you connect all these hydrogens together, like that, that's what you'd get. And that's called a tetrahedron, that kind of shape. It's a regular solid, which means it has 4 equal sides, equal angles, 4 corners. I don't know, you probably learned about it way back in geometry in 9th grade or whenever that is. But that is called the tetrahedron. That's why we call that shape, with the carbon atom in the middle. The importance of that shape is that bond angle is quite different than what we originally thought. See that? Oh, we'll stick with red. That bond angle is not 90 degrees. That bond angle is about, well, specifically it's 109.5 degrees. We could say about 110 or about 109. So much bigger than 90 degrees. The reason for that is we know electrons repel each other. They both have negative charges, and things with negative charges tend to repel each other. So in this structure, that allows those 4 hydrogens to be as far apart from each other as possible. And that's why it adopts this structure, because that's how those things can be as far apart as possible. So when we think about this structure, we're often throughout this chapter going to draw organic molecules that look like this. We're going to draw them flat because we got paper and it's a lot easier to draw things flat and try to draw some fancy thing like that. But we need to understand in our head that even though we draw them that way, what's really going on is this. That's the actual shape of this molecule, and that's the actual bond angle. There is a way that we draw this that, that can help us. One way that we sometimes draw it is, you'll notice we'll put the carbon there, the hydrogen, one of them going up and one of them going off to one side or the other. Kind of like this position right here. I'm going to jump back to that thing though. If we set this up so that, where are we? Here we go. So that one of them is going up and one of them is kind of going off to the left, and that's right in the plane of the screen there. That means that this one down here is kind of coming out at you. And this one behind is going back that way. Does everybody kind of see that in those 3 dimensions? The way we draw that in these structures is by using this wedge shape to indicate that one of them is coming out, and this dash shape to indicate one of them is going back. So we've got a hydrogen coming out toward us and going back away from us. And that'll be a way that we represent these sometimes. But if we're not really talking about the shape, we'll often see this. That also means that larger molecules, we're going to see larger molecules here, and those larger molecules are going to be also controlled by these same kinds of geometry. So if I add a couple more carbon atoms to my structure here, and then we take a look at them, you can see that a bunch of carbons in a chain is not really a straight chain, but it actually ends up being a zigzag because of that 109-degree bond angle. And you'll notice that each, if you kind of take a minute to look, each carbon here in that chain has that same geometry as just that single one in methane that we talked about. So they all have that tetrahedral geometry, which overall makes for this kind of a structure. So keep that in mind when we start looking at some of these bigger structures, because we're not necessarily going to draw them zigzag like this. We will often just draw them in a straight line, but it's important that we think about it really zigzag. And on Thursday, I'll have some models for you, and we'll kind of build some of this stuff and play with it, and you can see how it goes together. All right, so we have a sense of the shape of these things, of what this is going to look like when it gets a little bit bigger. So let's talk about some of these bigger molecules. One thing we do with organic molecules is we tend to group them into these broad categories based on what kind of atoms they're made out of and how those atoms are put together. Today we're going to start with the simplest ones, the alkanes, and then we'll go into some other ones probably on Thursday and then next Tuesday. So the alkanes, whoops, is a word that we give to molecules made of only carbon and hydrogen with only single bonds between the atoms. If we had any other atom, or if there's double bonds, then they're called, or triple bonds, then it's called something else. So these structures are only with carbon and hydrogen and only single bonds. And that gives us this really nice way of kind of building them up. And let's see, how many colors? I need one more color to make this look good. Let's see. It's a good color. Purple. Purple's good. Okay. All right, we're going to make ourselves a little table of some alkanes. We're going to build them up carbon by carbon. So we're going to start with a formula, a molecular formula. Then we're going to look at the structure. How are the atoms actually arranged with bonds in this molecule? We need to know what that name would be. And then we're going to look at this final thing called a condensed structure. As you'll see, as we get bigger, it's going to become really tedious to draw these structures. And so we have all these different ways, well, a couple different ways of shortening it and making it a little bit easier to draw without losing any information. And one of them is going to be called a condensed structure. All right, so we're going to start with our simplest alkane, which we already talked about, which is CH4. Its structure is a carbon with 4 hydrogens. And we're going to keep everything at these 90-degree angles just so it's really clear to look at. But again, we're going to know in our heads that that's not really what that thing looks like. It really has this other angle. The name of that is methane. And its condensed structure will also just be CH4. Condensed structure kind of assumes that we understand where the hydrogens go. And you'll see a little bit more about that in a minute. The next member of the series has the formula C2H6. That's 2 carbons connected together. And then we know carbon always needs 4 bonds, so we need to fill in the rest of the spaces with hydrogens. And the name of this molecule is ethane. Now its condensed structure, what we're going to do is condense the hydrogens onto the carbon that they're attached to. So the carbon on the left has 3 hydrogens, the carbon on the right has 3 also. We're going to condense those down to the hydrogens, and we're going to draw like this. CH3, CH3. That tells us that same information. It tells us that we've got 2 carbons connected with 3 hydrogens on the first one and 3 hydrogens on the second one. The only thing that's tricky about condensed structures is you have to know something about chemistry to really interpret them, because it looks like maybe you could draw that as C and then H, H, H all in a line. You have to understand that we know hydrogen only ever has 1 bond. So it's not going to be possible to put hydrogens in the middle of a structure like that, so they must go around the outside. And that's how the condensed structures work. You'll also sometimes see them with a line in the middle still. That's another type of condensed structure. Sometimes when we're looking at more complex structures, as we will later, it's helpful to actually have those lines instead of just smashing everything together like that. Sorry. So there's ethane. So we've got methane and ethane. The next member of the series is C3H8. You can probably start to see a pattern here. And this one's called propane. And since we've just done a couple, see if you can come up with a structure and a condensed structure for propane. It's going to be similar to what we just did. So hopefully you saw something like this. We got this chain of 3 carbons, and then we need to make sure they all have 4 bonds, so we have to fill in the other hydrogens accordingly. Then for the condensed structure, we're going to shrink or condense those hydrogens down onto those carbons and get something like this. Do something like that? Okay. Now for the fourth member of the series, I'm not going to tell you anything except that it's called butane. And based on the pattern that's already been established, see if you can fill in the rest of that. The formula, the structure, the condensed structure. Probably you want to do the structure first, and then come up with the formula by counting the atoms, and then see if you can do the condensed structure as well. All right, got some structure. So this one should have come out to C4H10 and look something like this. And you can see even in the fourth level here, it becomes pretty tedious to draw all these hydrogens. So these condensed structures start looking pretty nice. Another way we can draw this when we start getting these chains is you can actually make it condensed further. If you've got a really, really long chain, when you have things that repeat, like CH2 in a row, you can put them in parentheses and say, okay, we're going to have 2 of those. And so you might see something like that. All right, so there's a start for the first 4 of them. I'm going to pull up a table from the book so you can see some of the other ones, because it's going to take us a while if we keep drawing them like that. Whoops, missed it. Over here. We'll probably refer to this table a little bit today as we look at some bigger molecules. But here's how we figure the names of these larger ones. For alkanes, the class or the group of molecules are called alkanes. So we have this particular prefix that has to do with a number of carbons, and then we put ane on the end to be an alkane. When we look at different types of things in the next couple of weeks, different groups, it's going to follow that same logic, but the end is going to change. So instead of ane, it's going to be ene or ein or all, or there's going to be a bunch of them. But the prefixes for the numbers will stay the same. So we can check Blackboard to confirm, but I believe that you need to know these first 6. You need to know those names and those prefixes. The other ones you can probably figure out because they're a little more logical. They use the standard number prefixes, but I believe based on the course objectives that those are the ones that you should know. All right. Questions so far? Good? Okay. Next thing we're going to talk about is what happens when you have the same formula but different structures. The molecular formula that you see over on the right here is not as useful for organic structures as it is for inorganic structures. Most of the things we've talked about, like SO2 or NO3 or something like that, there's only one molecule that has that formula. So we use that molecule, it has a particular name, and that's that. With organic molecules, that's not quite the same because they're so much bigger. So we have these things called isomers. Isomers are structures with the same formula, so the same C whatever, H whatever, O whatever, whatever, same number of each kind of atom. But they're going to have a different connectivity, which means their atoms are connected in a different way. So the same atoms, the same pieces, as we'll see in those models, we'll use the same pieces, but can we make a different molecule using the same pieces? We're going to look at butane as an example here. And I'm going to use a couple different colors so you can really focus on the carbon chain. Here's butane again. And then let's draw a model of it in the thing here. Oh, I almost did it. Just get rid of one atom here. All right, so there's butane. Now, butane can be expressed in a few different ways. It can be rotated around. It can be, I can actually move this atom over here or something. Obviously, that looks a little crazy, but it's still the same basic structure. Right? So even if I pull that all the way over there, we're still talking about the same thing. We're still talking about 4 atoms in a row, CH3, CH2, CH2, CH3. Nothing's changed. These are not isomers. These are just different ways of kind of flipping around the same thing. But let's say instead, I disconnect that one. And I pull it over here. And I connect it to this one. Looks a little crazy. Where's the... Okay, there we go. Clean it up a little bit. Looks a little less crazy. So notice now this is different. I still have the same number of atoms. So I still have 1, 2, 3, 4 carbon atoms. And we can count them all, but you can just trust me that we still have 10 hydrogen atoms. But they're clearly connected in a way that's different from before. We now have this kind of, the longest continuous number of carbon atoms here is 3. You can go 1, 2, 3, and then you got to pick up your pen and get one over here. So they're no longer 4 in a row. Now we've got 3 and then this other one. There's no longer CH3, CH2, CH2. There's now a CH in the middle, see CH, and then CH3s around the outside. So let's draw this. It'll look something like this. And so these two molecules are called isomers to each other. They have the same formula. They're both C4H10. But they're different structures, they're different molecules, and their properties will be different too. They'll have different boiling points and stuff like that. So, so that's an important distinction. And now we're going to try this. You're going to try to find some isomers. Let's look at the isomers of pentane. Pentane is C5H12. So we want to find all the possible different molecules with a formula C5H12. I'll start you off with one of them. The easy one, where they're all in a line. And since this gets a little tedious sometimes, we might also use our condensed formulas for these too, which make it a little quicker to write. So think about the technique that I just used with that program, taking pieces off and attaching them on different areas, switching with hydrogen, and see if you can find some different structures besides this one that also have that formula C5H12. And keep in mind, you got to still follow the rules. Carbon still needs to have 4 bonds, and hydrogen needs to have 1 bond. So you can't just connect anything anywhere you want. If you think you've got one, come on up and draw it. We'll see how many we can collect. Everybody got one yet? Still thinking about it? Easy to check, and if it violates one of those, then you know it can't be isomers. These structures, I believe, all fit those rules. So then the next question is, are they isomers, meaning are they connected in a different way, or are they just the same, just drawn a different way? If we're looking for isomers, we want structures that are connected differently, not just drawn differently. So what do you think about these three? Are they all different from that first one that I drew? Are they all different from each other? Are any of them the same? What do you think?
I don't believe the last one isn't.
The last one isn't? What's wrong with that one? Yeah, if we think about the overall structure here, it's kind of like like that, like 5 carbons connected in a row. And this one is also 5 carbons connected in a row. So it's just like we took the ends of those chains and kind of bent them down. That's not a different structure. That's just rotating the bonds and kind of spinning around a little bit. So that's not an isomer. This one is not another isomer. It's the same as this up here. And that's the trickiest part of trying to find these isomers, is understanding when you've got two that are actually the same. That maybe they look totally different because you drew them in a zigzag way or flipped around backwards or upside down, but they're actually the same. So to find that, you want to look for things like how long is the longest continuous carbon chain? In both of those, it's 5. What about the distribution of hydrogens? You'll notice in these other ones, you've got things like CH3, CH3, and then CH, which is something that doesn't exist over here. So if you've got a different number of hydrogens on a carbon, that's got to be something different. Over here, we still have CH3, CH2, 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 CH3, which is what we still have up here. So that's going to be the same. And so this one, we found 2 different isomers from that first one, but that third one doesn't really count. These 2 do. They're both isomers. They are same formula, but they're connected in a different way. And this is part of what's difficult about this area of chemistry, is it takes a lot of kind of turning things around in your brain, thinking about things in 3 dimensions. There's not going to be any math here, but or at least maybe some geometry, not a lot of calculations, but a lot of kind of visualizing these complex structures and manipulating them in your head. And it's just something that takes practice. So that's why, just work on your homework and you'll get some good practice. Start a new page. The next thing we want to talk about, which I know is everyone's favorite, is naming. We're going to learn how to name these alkanes. We talk about naming rules for organic compounds the same reason we did with the inorganic compounds. Even though the rules seem complicated at first and seem like a whole bunch of rules that make no sense that just you have to remember, it's a whole lot easier than having to memorize a different name for every possible compound that there could be. So this way, there's a systematic way of naming so that anyone anywhere in the world can say, oh, okay, this is this thing's name, so then we know what its structure should be. So that's what we're going to look at with these alkanes. What structure, what's the structure, and how do we name it? All right, I'm going to list one here as an example, and we're going to go through carefully how we come up with a name for this structure. This is one of the isomers from above. There's going to be a series of steps that we use to do this. I'll write them over on the right here. So our first step for naming is going to be to find the longest continuous carbon chain. So you're going to look at carbons hooked together. How many carbons can you go before you reach the end? So in this example, what's the longest continuous carbon chain? How many carbons?
5.
Well, there's 5 carbons there, but how long is the longest continuous chain? Just 4, because you got to pick it up to get to that other one. That other one is hooked down at a different spot. There's a couple different ways you can count that. You can go 1, 2, 3, 4. You go 1, 2, 3, 4. You go 1, 2, 3, 4, or 1, 2, 3, 4. We'll talk about which one of those is better than another, but for this point, we just want to find the longest one. I'm going to pick one of these. I'm going to pick this as my longest chain. It doesn't matter because 4 is 4. I just picked that one because it's a little less obvious, and we want to have some practice looking at some of the less obvious chains as well as the one that's just straight across the middle. Because a lot of times that's kind of a trick, is that it looks like you should just pick the chain that goes straight across, but actually the longest one is one that kind of goes like that. So you gotta watch out for that. Okay, we've got the longest carbon chain, and the longest carbon chain is gonna give us the basis for our name. So how many carbons, so that's a 4-carbon chain. What's the name of something with 4 carbons? Remember from the stuff above? Butane, yeah, butane. So that means that the end of the name is going to be butane. So that longest carbon chain gives us that base name, gives us that basis, that end name. All right. The second thing we're going to do is we're going to number the chain. We're going to add numbers to the carbons. Let's not say try to, because you actually need to do it. Let's say number the carbons so that, I'm going to use a new word here, but we'll talk about it, so that the substituents have the lowest possible numbers. Now this word substituents. Substituents are the things that are not a part of the chain. So all the other stuff that's hanging off. In this case, it's just that one CH3 over on the left. That's not a part of that main continuous chain, so we call it a substituent. Just means a thing that's hanging off. So that tells us that if we want to number these carbons from 1 to 4, which carbon should we start at to make sure that, or which end of the chain should we start at to make sure that CH3 has the lowest possible number? We get 2 choices. We can start at one end or the other. Which end should we start at if we're going to number 1, 2, 3, 4 so that the substituent has the lowest possible number? Which one? The one lower, right. Because then we'll go 1, 2, 3, 4, and that substituent is on number 2. If we started on the other side, it would be on number 3. So we want that lower number. All right, so then the last part of the naming then is to identify and name the substituents with the number they attach to. So the substituents are going to be identified. I like to just kind of put a box around them. We know that's a substituent now. That's not a part of the main chain. And we have to figure out what kind of a substituent it is. So just as the chains take the name of however many carbons they have, the substituents are going to take that name also with one small addition. So we're going to define this. If you have a CH3 that's connected to something, we're going to call that a methyl substituent. So notice it's not a methane, it's a methyl. That YL tells you that it's connected to something, that it's actually a substituent. It's connected to some other chain. If we had a 2-carbon one, so if it were a CH3 and then a CH2 and then connected to something, we would call that an ethyl substituent, and so on. A 3-carbon one would be a propyl. There we go. So what kind of substituent do we have in our structure here? Yeah, it's a methyl, right? Just one carbon, a CH3. So that means that we're going to say methyl before the butane. But we also need to know where that methyl is on the chain. So which carbon number is that methyl attached to? 2. So we put a 2 with a dash, and that's the full name of that compound. This is called 2-methylbutane. All right, so we found the longest chain, we named it, we numbered the carbons of that chain, and then we added the substituents by name and by number. Let's try another one. Here's the other isomer that we looked at before. And let's see if we can use those rules again. So we'll find the longest continuous carbon chain. Where is the longest continuous carbon chain here? How many? 3, yeah, there's a bunch of different choices for those 3, right? You can go from up to down, you can go left to right, you can kind of go around the corner, however you want. And they're all actually going to be the same. So let's just pick the easy one this time. Let's pick this one. It doesn't matter. You pick whatever one you want. So there's our chain. Now we're going to number that chain. Does it matter if we start left to right or right to left in this case? Why doesn't it matter? Yeah, because the substituents are right in the middle. So either way, they're going to be on number 2. So 1, 2, 3. Okay. And then finally, we find our substituents right here and right here. Now this time we've got 2 substituents, and they're both methyl. Oh, so we forgot to write down our name. What's our name for the 3 carbons? Propane. And now we have 2 methyl substituents. So we don't say methyl methyl, we say dimethyl. For 2 of them. If there were 3, it would be trimethyl and so on. And then once again, we have to say where those methyls are. They're both on carbon number 2, and each substituent gets its own number. So this one is named 2,2 dimethylpropane, or 2,2-dimethylpropane. All right, so each substituent needs its own number, but because they're both methyl groups, we kind of group it together. And we say 2,2 and then dimethyl. All right, let's try some more. So see if you can do this one. Take a look at, I can't quite get those rules on the screen still, but hopefully you've got them on your notes. So you're going to find the longest chain and name it. Then you're going to find the substituents and name them and the carbon numbers that they're on. Give it a try and we'll see what you come up with, and then we'll look at it together.
When the last one, CH3.
Oh, yeah, thanks. Sorry. Missed a 3 there. All right, so where did you find the main longest chain to be? There's a few different choices here. How many carbons did you find? 4. So 4 is the longest chain. Where did you find your 4? You kind of draw it. There's a couple different ways to do it. You could go like this, you go like this, you go start here and go like this, or like this, or like this. So it should be all the same. So however you like to pick your 4, I guess I'll pick this one. Now we need to number that chain so that the substituents have the lowest possible numbers. Where do we start to do that? We're going to start that top left or at the bottom? It doesn't matter, right? Because this one's actually symmetric. So either way, substituents will be attached to the second and third carbon. So we'll go like that. Okay, so now we're ready to write the name down. What is 4 carbons? We talked about that. That's butane. And then we've got 2 methyl substituents here and here. So that's going to be 2, 3. I'm going to run out of space. Dimethyl. 2, 3 dimethyl butane. We have 2 methyl groups, substituents on 2 and 3. So we write 2, 3 dimethyl butane. That's our name. So did you get something similar to that? Different? You may not sure why yours was different from what we came up with up here. Okay. Let's look at another one. See if we can do that one. I just got a good name for this one. Something good? Sorry, keep working on it. A couple more minutes. All right, we get a name? What do you think? Want to try one? Everybody's like, I know you all have names for this, but nobody wants to volunteer.
3-ethyl pentane.
3-ethyl pentane. Let's see. All right, well, we can check this. So a 3-ethyl pentane should mean the longest chain has 5 carbons. I think I see that. You like that? And then an ethyl group on the 3rd carbon. So that makes sense. There's a 2-carbon group coming off of that 3rd carbon. And so that's an ethyl. So yeah, 3-ethyl pentane. Sounds good. Other people get that also? Yeah.
Okay, so I got that, but I just drew it a different way, so it doesn't matter.
Shouldn't matter, no.
Okay.
The only time that choosing a different chain is wrong, well, 2 times. One, if it's not big enough. So like if you pick the chain going straight across, that's just 3. That wouldn't count because it's got to be 5. Or if one chain makes the substituents at a lower number than the other, you should pick the one that makes them at a lower number. In this example, it didn't matter. So anywhere you picked it would be fine. Yeah, as long as you came up with that name, good. So this also tells us a nice way to solve this previous problem of figuring out the isomers. If molecules with the same formula have different names, then you know they must be isomers. Another way to do it, assuming you're naming them correctly. So rather than trying to figure out, oh, is this different or not, one example is with these 2 that we found out were the same, they both had the longest chain as 5 carbons with no substituents. So that tells you that they're both named pentane, just plain old pentane, and therefore must be the same. They don't have any substituents. Okay? All right, keep working on this. There's plenty of practice in the book. With the last 5 minutes, I want to take a look at the lab, just because it's easier to talk about it with everybody down here instead of